All right, so using the RA game, we've now come to understand how students can fill up a dormitory. In the same way, electrons fill up these microscopic little dormitories, which is what we call the energy levels. So I'm going to show you guys how to graphically show how the different electrons fill up these dormitories. We will start with hydrogen. We're going to do the first 11 elements. Hydrogen has one electron. How do I know it has one electron? Because the periodic table says 1. That's its atomic number, 1. Okay, so how many rooms will our dormitory have?
1.
You just need one room. And what we need to do is let's see, 1s, draw 2s, 2p, and 3s, so that we have somewhere to place these dormitories. Okay, so one room. In order to show that we have one electron there, what we're going to do is we're going to draw a half arrow. Just a half, one prong on that arrow. That shows that we have one student in there. Is hydrogen happy? Is it a happy RA? No, why not? Okay, it only has one floor and one room in that floor, and that's not filled up. So, what kind of deals do you think hydrogen would want to make with people around it? Okay, so it could take an electron in order to fill it up. That would make it a -1 charge. What else could hydrogen do in order to get his $1,000? Give. Make this guy disappear, which would make it what charge? So what do we find about hydrogen? Hydrogen most of the time is +1, but sometimes it can be -1. How about helium? Helium is atomic number 2. It has 2 electrons. Okay? So, how many rooms will you need to satisfy those 2 students? 1. Now, according to Hund's rule, which we studied yesterday, you can have 2 electrons in the same floor. You can even have them in the same room, but they can't be in the same place at the same time. According to Hund, while one electron is spinning clockwise, the other one has to be spinning. So how can we show that these electrons are living in a teeny tiny little cramped area, but they're not in the same place at the same time? And that's why it's half arrows, so that they can fit together. Okay. Lithium is number 3. Oh, I'm sorry. Let's go back. So, tell me about helium. Is helium's RA? Tell me about helium's RA. They're happy. Did they get the $1,000? Yeah. Yes. So, will helium want to lose any electrons? No. Gain any electrons? No. Helium is completely what we call inert. It's a noble gas. It doesn't want to react. Now, do you understand why helium doesn't react with anything? Okay, lithium. How many rooms will lithium have to have? No. 5. Why? You got to open the first floor, right? But when the second floor opens, now, how many rooms does lithium need? 2. It has to have 5. How many does it need? There's 2 and then 1 more. Somebody, talk to me about lithium. How happy is lithium? No. Let's see. Somebody besides Ryan. He's already answered one of these. Somebody else. Max, go. Or you can gain You can gain 7. How likely is that going to be? Well, it'd be much easier for lithium to do. So when lithium reacts, what kind of charge will it tend to have? -1 means you gained a negative. Ah, did you ever wonder why lithium was +1? Simon.
Is it possible? I mean, it's not like
Too much energy. Yeah, too much. It would take too much energy. Beryllium, number 4. How many rooms does beryllium have to have in its dormitory? 5. Still 5. But how many rooms does beryllium need?
2.
Just 2. Arrow up, arrow down, right? Then 2 more. In the same room? Yes. You gotta fill up the S before you can go to the P. All right. Is beryllium happy?
Yes.
And you got to look at this point now, you have to look at these. Is it happy?
No.
No. Why?
Because
It has 2. The spa room is full, and that's good.
but the rest of the floor is.
How many more students does he need to be happy? Or he could. So what's the charge on beryllium according to a periodic table? Yeah.
Mr. Moreno,
Yes.
if this works, how come copper can be
I'll explain that to you. That's a good question. Patience. Boron, 5. How many rooms do you need? How many rooms do you have to have? How many rooms do you need? 3. 1, 2, 3, 4, 5. What do you need to do, Allison, in order to be happy? Or what's more likely to happen? And according to your periodic table, what's the charge on boron? Wow, this is working.
How do you know how many rooms it needs?
Because once you open up a floor, you open all the rooms up.
Okay, but how do you know how many students are like
The atomic number.
okay.
So since you have to have 5, there's 2 right here, 2 right here. You could potentially have 6. The 5th one's going to have to go in that section. All right, be careful. This one's hard. Allison, how many? Carbon has how many? So how many rooms do you need?
You need 5.
Are you sure about that?
No, because you're saying 3.
All right, let's just do it. First 2 go where? First 2 go where?
Oh, first 2 go where in the first one?
Next 2.
And in the second one?
Next 2.
And the first one and that 3.
Actually, you forgot the rule that we used in the RA game. You could only have one. Hold on a second. I said it wrong. The rule that says that allows you to that makes sure that you have to have one arrow up and arrow down is Pauli's exclusion principle. Hund's rule is something we've not gone over. Hund's rule states, Allison, that when you're placing electrons in the orbitals, you have to place them one at a time in the same direction until you have no other choice but then to double them up. And the reason why this is important is because this helps us to predict whether something's going to be magnetic or not. The more single people we have, the more magnetic a substance is. It's a special type of magnetism called paramagnetism. Okay? So this guy is more magnetic than boron because it has 2 solos. Okay? What about carbon? Allison, is carbon happy?
No.
How many would it need to take?
4.
How many would it need to give?
4.
Because it's right in the middle, it tends to do neither. It tends to share electrons. That's why we rarely ever see carbon in an ionic compound. It's right in the middle. How about nitrogen? Molly, describe it.
It's
7. Molly, go.
4.
Huh? What? Okay, 4 rooms. You sure about that? Let's start right here. How many go there? How many go here? How many go here? How many go here? This is 6. And how many go here? So you needed how many rooms? 5. How magnetic is nitrogen compared to carbon? More. Oxygen. Are you beginning to see the pattern? Mark, go.
Alright, so 2 in that one, 2 in the next one, 2 in that one, 2 in the next one.
Is oxygen magnetic? Yeah. Okay, let's go back to nitrogen because we forgot something. Molly, how close is it to being happy? Or it could lose how many? Well, if you lose 3, you still have these 2. Okay, 5. So you can either gain 3 or lose 5. What do you think you're going to do? What would be easier for you to do? And that is why nitrogen is -3. What about this one, Mark? Lose 2 or gain 5? I'm sorry. Yeah, lose 5 or gain 2. And that's why oxygen is -2. Fluorine. 9. Describe it, Natalie.
There's 2 in there,
That's 2.
and 2 in there,
That's 4.
2 in there,
6.
yeah, and 2 in there,
8.
and 1.
Yes. How desperate is fluorine?
It just needs 1.
It's going to be desperate.
Yeah.
Is this an element that you would be afraid of? Because what would it be trying to get from you desperately?
An electron.
An electron. And that is why fluorine is so dangerous. Because how desperate is it? Very. Well, how desperate is it to lose 1? Yeah. Yes.
Is that why the halogens are so reactive?
Yes. Because they all come close to finishing the sequence, but not finishing it. All right, Alec, neon.
2 in there. 2 in there. And 2 in all 3.
Talk to me. Would you want to play with neon? Neon's a gas, but
Yeah.
why?
It's not gonna do anything.
Why not?
It's not gonna
So why are the noble gases harmless to us? They fill up, they complete the cycle.
So if you like read the yellow,
Won't hurt you. Now, radon is the only one that could potentially harm you because radon is a radioactive element. So if it was to blow up inside your lungs, then it would stay there as a piece of solid. And then that solid could further blow up. And by explosions, I'm talking about teeny tiny, minuscule explosions that you would never feel. All right, how about sodium? Ruthie, how many dorms do we need? Up until now, it's been 5. But all of them have been filled up. Sodium has 11. So how many dorms do we need? Good. What would be more than 5? No. Once, let's see, this is 1s. Second floor is complete with 2s and p. 3s. The third floor, s. Actually, you need 4 more. No, you have to have 4 more. How many do you need? Just 1 more.
Wait, but you just opening the S, so why is that you
What?
Oh, because you gotta open up everything.
Actually, in theory, you should also be opening up the 5D rooms. Okay, so how desperate is sodium? Ruthie, what does sodium want to do in life? That's right. So sodium is crazy. It is a maniac. It's desperately wanting to lose 1 electron. And in nature, we will never find it by itself. We'll always find it where it has already lost it. It's that desperate. It'll react automatically. We have to force it to accept an electron back with electricity. We basically ram an electron down its throat. Okay, do chlorine by yourself. 17. Chlorine is 17.
Those little arrows represent,
Electrons.
like, is there any difference?
While one is spinning clockwise, the other one's spinning counterclockwise. Pauli's exclusion principle. All right, is that what you guys got? So when sodium meets chlorine, what will happen?
Sodium will give it its electron.
A reaction occurs, and then they stick together. Because this becomes negative, and this becomes positive. And that is why they do what they do. Now, orbital diagrams are really cool. They can help us understand whether something's magnetic or not. They can really clearly help us understand how stable something is and whether it's going to give or take away electrons. But how about if you want to do the orbital diagram for uranium, number 92?
Spinning a lot of boxes.
Okay, so that can be a really long, arduous thing. So when we meet again, I'm going to teach you a shortcut to this to help us deal with the very large atoms like uranium. And even that shortcut will take us a long time, so I'll teach you a shortcut to the shortcut. And even that shortcut takes us some time, so I'll teach you a quick and easy way of doing it, which is the shortcut to the shortcut to the shortcut.